I'm Yi Yu from the University of Warwick, and I will be chairing today's webinar. The RSS webinars aim to acknowledge past papers in the RSS journals with high influence and to shed light on current and future research through reflections and discussions. The session today is on the change point detection, which can be dated to the World War II and which is gaining increasing popularity these days. It is our great honor to have two presenters and discussants today. Professor Paul Fearnhead from the University of Lancaster will talk about the univariate online change point detection problem in a Bayesian framework. Dr. Tengyao Wang from the University College London will talk about the high-dimensional offline change point detection problem in a frequentist framework. Professor Claudia Kirsch is our discussant today. She's from Otto von Guericke University, Magdeburg, and she will be our discussant later.
So this is a talk based on a paper called Online Inference for Multiple Changepoint Problems, which was joint work with Zhen Liu, who at the time was a PhD student with me at Lancaster University. So an overview of the paper is that it describes how to do Bayesian online inference for changepoint problems. And there were sort of two main motivations for the work. One was applications where you want to do the analysis in real time, so you do need an online method. And the second motivation was more how can you do Bayesian inference in a computationally efficient manner, particularly if you think about applications for big data. So looking back, I think big data in those days is quite different to what we view as big data nowadays. Now, one of the things which makes the paper sort of distinctive from a lot of the current work on sort of change point methods, and for example, distinctive from the topic of the second talk in this webinar, is that it presents a Bayesian approach to the problem. And before I talk about the paper, I thought it would make sense just to make a couple of comments about what are the benefits or disadvantages of being Bayesian in terms of trying to estimate or detect multiple change points. And there's basically a couple of points I want to make. So the main difference when you're being Bayesian is that you're having to specify a prior for parameters in your model. And so, and the disadvantage of being Bayesian for the change point problem is that the results you get can be quite sensitive to the priors that you choose. And in particular, you have to be careful with how you choose the prior for the segment specific parameters. Okay, so we're going to have a situation where we have a single data set, but then we estimate lots of changes, and the changes will split the data into lots of segments. And within each of those segments, there's going to be a different parameter, and we're going to have to specify a prior distribution for those parameters. Okay, and if you choose that prior badly, you can get very poor results. And in particular, you have to be careful that the sort of natural thing to do often is to think, well, you know, I don't necessarily have much prior information. I'll just use an uninformative prior or a vague prior. And if you do that in this situation for the segment parameters, that will tend to mean you massively underestimate the number of change points. Okay, so you really need a sensible prior for the segment parameters. Okay, the benefit or the positive story, though, is that that prior distribution is actually sort of capturing something sort of observable in the data, and therefore you can actually use the data, for example, within an empirical Bayes approach to actually make sure that you have a sensible prior. Okay, and what I mean there is that that prior on the segment parameters is sort of trying to model or capture how the parameters vary across segments, and that is something that there'll be information in the data. And the advantage of the Bayesian method is that it potentially uses that information, and using that information can lead to sort of more powerful inferences. Okay. But if I now go on to talk about the sort of content of this specific paper, what I thought would help would be to start off with an example application, just to try and sort of make it clear the sorts of problem that we're trying to tackle, and then go on to the sort of more algorithmic aspects in the paper. So one sort of application of changepoint methods is the following. So this is taken from genetics, and it's looking at the problem of trying to model divergence between two strains of something, and in this example, I've imagined two strains of Salmonella. Okay, so where the data comes from is that we have two distinct strains of Salmonella. We sequence them and we align those DNA sequences, and then as we go along the genome, we sort of just record how many nucleotide differences there are between the two aligned sequences. Okay, and the reason that this is interesting in it is that that data is informative about the sort of ancestral relationship, or how closely related the two strains are, and how that ancestral relationship varies along the genome. So sort of pictorially, we have a situation like this, where I've imagined I've got two strains, typhi and paratyphi A. I have sequenced parts of their genome and aligned them. Okay, and the idea is that because of a process called recombination, the sort of how closely related the two strains are will vary as we go along the genome. Okay, so in this case, I've imagined recombination means that there's sort of 4 different parts of this region of the genome, each with a different sort of ancestral relationship. Okay, and then the data, which is the number of nucleotide differences, it is sort of gives us partial information about this, because we have the property that in regions where the strains are distantly related, we'd expect to see a higher number of differences, and in regions where they're more closely related, we'd expect to see fewer differences. Okay. So one way of modeling this is the following sort of simple hierarchical model, which sort of says, so we have our data, and the data actually, you know, we have these aligned DNA sequences, we split those into 100 base pair windows, and the data is just the number of differences within each of those 100 base pair windows. Okay, and a hierarchical model for the data would be to say, well, the top hierarchy is that there's going to be a random number of change points which will split my data into segments. For each of those segments, there's then going to be a sort of parameter beta, which governs the sort of mean divergence in that segment of the genome. And then for each of the windows within that segment of the genome, I'm going to then generate another parameter theta, which is the expected number of DNA differences within that window. Okay, and that will be centered, that will have a mean which is dependent on the beta parameter. And then finally, the data itself is Poisson with mean theta. So pictorially, the hierarchical model is as follows. We have our region of the genome. We first of all have a number of changes which split the data into segments, in this case 4 segments. For each of those segments, we will have a segment-specific beta parameter which will determine the sort of mean divergence in those regions. Then for each of the windows within each of the segments, we'll generate a sort of theta parameter, okay? And then the data is just Poisson, IID Poisson, with mean given by each of the individual theta parameters, okay? And in some sense, the challenge is that the data we observe is just the sort of stars, the black stars in this diagram, and from that data, we want to really infer maybe the segmentation and also what the segment-specific parameters are. Okay. Okay. So that's one example of an application and model where the sort of following algorithm can be applied. But if I now describe the sort of setup a little bit more generally, the general setup is that we assume that there's, we're analyzing a change point model. The model will have a set of change points. The number of change points m is unknown, and the location of the change points is unknown. Okay. If you were told the change points, that would split the data into m+1 segments. Each of those m+1 segments will have its own segment-specific parameter, okay, drawn IID from some prior distribution, and then conditional on the segments and the segment-specific parameter, there'll be some likelihood model for the data within each of the segments. And the likelihood for the data within the ith segment will only depend on the segment-specific parameter for the ith segment. Okay. Okay. And I really want to sort of draw out two aspects that are sort of key to the sort of algorithm I present working. One of which is a sort of consequence of the setup of the model that I've just presented, and one of which is a sort of further assumption that we need to be satisfied. Okay, so a consequence of the way of the sort of model I've described is that in many cases it will have a sort of conditional independent structure, which is sort of mathematically represented here, but it's sort of saying that if you were told that there's a change point at some specific point tau, then conditional on knowing that change point, the sort of likelihood or the probability of the data prior up to tau would be independent of the data after tau. Okay, and that sort of conditional independent structure is really key to the sort of algorithms that I'm going to describe. And the other thing which I'm going to assume is that I can integrate out the segment-specific parameters associated with any given segment. Okay, so if, for example, I know that there is a segment which starts at time s and ends at time t, okay, then I'm going to assume that I can analytically calculate the marginal likelihood for the data within that segment, given it is a segment. Okay, and this marginal likelihood is just equal to the integral of our segment-specific prior times our likelihood. So I'm essentially assuming that I can do that integration analytically. Okay. Right. And what I'm going to present is a sort of online algorithm. So, so in general, we're being Bayesian. So in general, what we're going to be interested in doing, maybe in terms of sampling from the joint distribution of the number and location of all the change points. But the way I'm going to present this sort of algorithm for doing that is, first of all, in terms of calculating a sort of marginal distribution. But it turns out that if I can calculate all these different sort of or univariate distributions, if I can calculate all these univariate distributions, then it's essentially for free. It's possible to simulate from the joint posterior. Okay, so the thing I'm going to focus on is at any time t, I'm going to introduce a state variable ct, which is just the time of the most recent change point prior to t, and I'm going to be interested in calculating what's the sort of posterior or the conditional distribution for ct given the data up to time t. And essentially what I'm going to present is a way, so this distribution is often called the filtering distribution, and what I'm going to try and describe is an algorithm for recursively calculating this filtering distribution at successive values of t. Okay. Now, if we think about this variable that I've introduced, ct, it's quite easy to see that we can write down conditional distribution or transition density for ct plus 1 given ct. Okay, and essentially the idea here is that if we go from time t to time t plus 1, there's only sort of two possible things that can happen. Either there isn't a change point, in which case ct must be the same as ct plus 1, or there is a change point, in which case ct plus 1 must be equal to t. Okay, so if I consider this conditional distribution here, it's basically just going to have two possible values which correspond to whether or not there is a change at time t or there isn't a change at time t. Okay, and the actual values of these probabilities will depend on my specific sort of prior model for how many change points there are and where they occur. Okay. And then similarly, there's a way of then getting a recursion which will relate the sort of filtering distribution at time t plus 1 in terms of the filtering distribution at time t. Okay. And on the slides, I give the expressions, and in some sense that, you know, that the exact derivation of these isn't too important, and it's described in the paper. But if I just try and describe the sort of basic intuition behind these, and I mean, hopefully it sort of should be relatively clear, and deriving these is pretty straightforward. So essentially, there's two equations here in the recursion, and again, these just correspond to the two possibilities of either there isn't a change point at time t or there is a change point at time t. Okay, so the first of the expressions corresponds to there not being a change point at time t, and in that case, ct mistakes the same value as ct plus 1. Okay, so that's why we've got you know, so if we're calculating the probability ct plus 1 is equal to j, given the data up to time t plus 1, we can relate that to the probability that ct is equal to j, given the data up to time t. Then we need to multiply that by the probability there's no change at time t, and then using Bayes' theorem, we then multiply it by a likelihood term. Okay, and the likelihood term is this sort of ratio here, and that which is just in terms of a ratio of these marginal likelihoods that I've assumed that we can calculate. Okay, and you get a very similar recursion in the case where there is a change point, and the only difference here is that if there is a change point at time t, the value of ct could be anything, so you need to sort of marginalize over all possible values of ct. Okay. So in some sense, the take-home message from this previous slide was that you can write down relatively easily these recursions for these filtering distributions, and then it turns out that it's straightforward to solve those, because the distributions of interest are distributions for a discrete random variable which takes a finite number of values. Okay. So one way of doing that, which has allusions to what people do in particle filters, is that we can represent this discrete distribution, this discrete filtering distribution, the CT, in terms of a set of possible values of CT, which we call particles, and a set of probabilities associated with these, which are often called weights. Okay, and so the slide just introduces the notation for the particles and the weights. Okay, and essentially the previous recursion just gives us a simple way of updating the particles and their weights from time t to t plus 1 and so on. Okay, and so it's quite easy to solve that for t going from 1 up to capital T, just to calculate all these different filtering distributions. And then I won't give the details, but once you have those, it's straightforward and very quick to actually obtain IID samples from the joint posterior. Okay. So that's sort of an online algorithm, but it has sort of two drawbacks, related drawbacks, and that is that the computational cost per iteration of this algorithm depends on the number of particles you have, and the number of particles increases linearly with t, because at time t there's t possible values for the most recent change point. Okay. And so that's not good for an online algorithm where you may have a fixed amount of computation per iteration, and it's not good for in terms of computationally efficient algorithm, because the computational cost for analyzing capital D data points is now quadratic in T. Okay, so the idea in the paper of avoiding this is to introduce a sort of resampling step. And the idea here is that we're going to replace the weights associated with each of our particles by the realization of a random weight. And these random weights we're going to want to have two properties. One is that they're unbiased, and secondly, that with some probability, the random weight is going to be equal to 0. Okay, and the latter property is really the key to reducing the computational cost of these algorithms, because if we generate a random weight which is 0, then in some sense we can remove the associated particle. That will reduce the number of particles we have to keep and speed up the algorithm. Okay, and obviously there's lots of ways of doing the resampling, but there's one specific approach presented in the paper, which has quite a simple idea, and I'll try and describe that in pictures. And that is that the sort of user has to choose some sort of threshold alpha, okay, which will govern the level of approximation error resampling has. And then the way the resampling works is that, first of all, okay, so in the top plot, I've imagined I've got a set of particles ordered in value together with their associated weight. And the first step of the algorithm is that you just look at which particles have a weight greater than alpha, and you keep those. Okay. What you then do is you then resample the particles whose weight is less than alpha in such a way that the marginal probability of resampling them is the weight divided by alpha. But you do the resampling in a stratified way, so that if you sort of resample one value, you're less likely to resample neighboring values. Okay. And then finally, what you do is you throw away all the particles you don't resample, and you increase the weight of the particles you do resample to alpha. Okay. And there's some nice sort of theory which shows that the choice of alpha is directly linked to the sort of approximation error you introduce by resampling, and you can sort of show that this is, in some sense, the best approach to resampling given a fixed level of approximation error. And the other thing which is nice in an offline setting is that the way the algorithm works, the number of particles you end up resampling at each iteration is random, but in a way that, in a sensible way, or in a data-driven way, so that in sort of situations where you need lots of particles to approximate the filtering distribution well, it will keep lots of particles, and in situations where you can approximate the distribution well with few particles, it only requires a few particles. Okay. In an online setting, that the randomness in terms of the number of particles you have often isn't good, because you may have a fixed budget per iteration, but in those situations that there's a variant of this which means that you end up using the same number of particles at each iteration. Okay. So given time, I think I'll skip a lot of the examples, just showing some of the properties and showing that this resampling can be more accurate than alternative resampling algorithms that exist. Okay. I'll also skip, just very briefly. So since this paper appeared, we've looked at various extensions of it, and in particular, there's sort of two basic ways of trying to extend it. One is looking at models where you can't analytically calculate this marginal likelihood, and in that case, often you can get a good version or an accurate version of this algorithm to work just using a numerical approximation to the marginal likelihoods. And the other way is to try and deal with sort of dependence across segments, which mean that this sort of conditional independence property no longer holds. Okay, and there's a nice paper which looks at dependence across segments, which can be modeled via a hidden Markov model. And in that case, you can still do things exact using the ideas in this paper together with ideas for filtering for hidden Markov models. Okay. So I'll just skip to the discussion. So there were just sort of two final points I wanted to make. but given time, I'll just focus on the last of these. So, which is just so being Bayesian. One of the benefits of being Bayesian is that the methods naturally quantify uncertainty. Okay, because you get the posterior distribution, and sampling from the posterior enables you to sort of quantify uncertainty. And often quantifying uncertainty in change point problems is very challenging. Okay, as far as I see, the main issue with using these Bayesian methods in terms of quantifying uncertainty is really a question of often the models you fit have relatively sort of have quite simple model assumptions which you may not fully believe, and therefore often sort of point estimates can be quite robust to such model errors, but measures of uncertainty and the measures of uncertainty you get from the Bayesian posterior probably wouldn't be. So I think one of the main challenges going forward with Bayesian methods is how do you implement them in a way that you actually get the full benefit from being able to sample from a posterior distribution, in the sense that the measures of uncertainty are robust to modeling errors. Okay, but I think given time, I'll stop there. Thank you.
Basically, I'll be talking about this paper, high-dimensional change point estimation via sparse projection. So it was a joint work with Richard Samuels from University of Cambridge. As E mentioned at the very beginning, this work is different from Paul's earlier talk in a few aspects. And probably the most obvious one, if you just look at the title, is that we are dealing with high-dimensional data. So maybe I'll start by saying a bit about why are we interested in high-dimensional change points. The main reason is that there's a kind of an increase in the amount of these high-dimensional time-order data sets that we're getting nowadays. So I have two pictures here. One of them, the left, is about many internet routers around the world collecting internet traffic data, so that you can view as a high-dimensional time series, because the many different routers are representing the many different dimensions. And on the right, you have the kind of an example of an fMRI data set. So very briefly, fMRI records the kind of a level of some chemical contrast in different locations of the brain, which we call the voxels. And then essentially, fMRI data sets are voxel time series co-evolving through time. But these are just the classical examples of the so-called high-dimensional time series. I mean, nowadays we're in the Internet of Things age, and it's much easier and cheaper to collect such high-dimensional time series data. For example, we have all the sensors connected to the internet, and you can talk about things like wearable medical devices, sky surveying telescopes, and or microsensors measuring the structural safety of buildings. And we have all these high-dimensional data streams everywhere. And the natural question is what we can do about them. A common feature about high-dimensional data sets is heterogeneity. And for data streams, this is typically manifested through non-stationarity. Because when we have so many different component series, it's not easy to believe that all of them are stationary. And in fact, non-stationarity can actually represent features of interest in many applications. And that's where the change point analysis comes in, because change point analysis can be used as a first step towards handling this heterogeneity by carving the long time series into shorter segments that are more or less stationary so that we can analyze them. And also these estimated change point locations may be of independent interest themselves. So here's a quick survey of the landscape of the change point literature. It goes back all the way to, I think, at least 1955 by Page. Just one thing, I think another difference between this work and the Paul's is that I think we deal essentially with offline change point estimation, where we know the kind of the whole data set before we perform the analysis, instead of the online version that Paul deals with in his earlier work. So the literature I listed here are all about offline change point estimation. So in the univariate setting, the current state-of-art method includes the PELT algorithm, which is by the Lancaster group by Killick, Fearnhead, and Ackley, and then the wild binary segmentation method by Frislevich, and also the smooth algorithm by Frick, Monk, and Sealing. So these are just a few different methods that achieve very competitive univariate offline change point estimation. And some of these univariate change point methods have been extended to multivariate settings. But at the point of writing of this paper in, I think, 2017 or 2018, there wasn't that much done on high-dimensional change point estimation. By high-dimensionality, I mean here that the number of component series is of comparable or even larger order than the number of data points we have. And that's why we studied a new method called InSpec that uses convex optimization to try to estimate change points in high-dimensional regimes. Paul has described this setup for change point estimation. So this is actually quite similar. We use slightly different notation in our paper. So essentially, the setup here is that we observe data points x1 up to xn. And here, these x1 up to xn are p-dimensional random vectors. And then we organize them into, arrange them into a data matrix X. And then the slight peculiarity here is that the rows, we have p rows and n columns. So it's slightly different from the traditional high-dimensional setting. So the time goes from left to right, and then the rows represent different component series. So these x1 up to xn are independent with piecewise constant mean structure. And then the mean vectors mu t undergo changes at time points z1 up to z new. So there are new change points in total, and these are unknown, and we also do not know the number of change points. So we want to use the data to estimate both the number and the location of these change points. For notational purpose, we record the the common mean between the ith and I plus first change point as mu of I, and then the vector of change in the mean after and before the ith change point, we say that's called theta superscript I. And we make a few additional assumptions. The first assumption is a sparsity assumption. We say that even though there are a large number of coordinates that can potentially change, but at each change point, only a small number actually undergoes a change. So this is a reasonable assumption in a lot of real-world applications. For instance, if you think about the fMRI dataset we saw earlier, the brain activity may only affect a few different brain locations. So the change in the brain activity may only be in a few different brain locations. And also in the internet traffic data, maybe some distributed denial of service attack may only be initiated by a few, be recorded by a few routers in the internet. And this is actually will be an essential assumption later on. You'll see that in high-dimensional settings, we can't do much without these sparsity assumptions. And we also make a minimal signal strength assumption. So this var theta, the character var theta, is denoting the lower bound for the L2 norm of the vectors of change. And the tau here characterizes the minimal stationary run length between consecutive change points. Right, so that's the model assumption. We use the set curly p with these model parameters to denote the set of distributions satisfying these above assumptions. Of course, in practice, we do not expect our data sets to satisfy all these assumptions. The assumptions are here more as a way to motivate the algorithm and also to facilitate its analysis, rather than we really believe that these are necessary. So we will characterize the performance of the algorithm theoretically under this set of distributions. So I'll structure the talk in the sense of us first describe how we can estimate a single change point, and then we can go on to talk about how we can estimate multiple change points using this single change point estimation procedure. In the single change point setting, in the under the notation we had before, the nu, which is the number of change points, is equal to 1. And for simplicity, we just write z for z1, theta for theta1, and tau, which is the a minimal stationary run length, is going to be the minimum between z and n minus z divided by n. Our data matrix X can be decomposed into, well, the mean matrix mu plus the noise matrix W, where according to our model, it's going to have IID normal 0 sigma square or normal 0, 1, I can't remember whether I've normalized the variance or not. I think I've normalized the variance. So it's normal 0, 1 entries in the W matrix. And then you can see that the signal is scattered across a few different components in this data matrix X. So one way to aggregate the signal and borrow strength across different components is to try to project the data matrix X along a certain direction, a p-dimensional vector, so as to kind of generate a one-dimensional data series. And we want to find a projection direction that maximizes the signal-to-noise ratio after projection. And if you kind of play along this data set a while, it's not hard to see that the optimal projection direction is going to be parallel to the vector of change, which we call V here. So that's a unit vector parallel to the vector of change theta. So if we can estimate this V well, we are going to be in good shape. Of course, the kind of a catch here is that in high-dimensional settings, it can be shown that it's impossible to estimate V consistently if you do not impose additional assumptions. And that's why the sparsity assumption is needed here. So how do we exploit the sparsity to estimate the projection direction V? One natural thought is to say that, well, the columns of X here can view this as coming from kind of a mixture of two different Gaussians, and then maybe we can use some sort of like a clustering, or maybe even use sparse PCA to find the direction where the data varies the most. However, using sparse PCA or the related ideas ignores the fact that there is a temporal relationship between the different consecutive data points here, because it essentially treats the columns of X as exchangeable. And that's an inefficient use of temporal information. So it turns out that the best way to use both the temporal information and the spatial sparsity information is to first perform a Q-sum transformation on the data matrix X before exploiting the sparsity structure. So the Q-sum transformation is a well-known transformation for offline change point estimation, even in the univariate case. So basically what happens is that we're going to apply the transformation to the data matrix X row by row. So basically we're kind of doing a univariate change point transformation for each row. And for every row where we have n-1 potential candidate change point locations, and at every candidate change point location T, we calculate the difference of the mean to the right and to the left of that candidate change point, and rescaled appropriately so that under the null, where there's no change, this distribution will actually be normal 0, 1. So I mean, the bottom line here is that this transformation, the Q-sum transformation is a linear transformation. So when we apply the Q-sum transformation to the data matrix X, we can write this as the transformation of mu plus the transformation of the noise W. And the benefit of doing this is that, well, we see much more pronounced signal in the transformed the mean structure. And it's not too difficult to analyze the Q-sum transformation of the noise either. We give names to these three matrices. We call the Q-sum transformation of data T, the Q-sum transformation of the mean A, and the Q-sum transformation of the noise E. Right, I mentioned earlier that the Q-sum transformation of the mean, which is denoted by A, has a much more pronounced signal. And actually, you can write down this matrix A explicitly because we only have one single change point. And this matrix A, it turns out that it's actually a rank 1 matrix. Moreover, the leading left singular vector of A is the oracle projection direction V that we are interested to estimate. So if we don't have access to A, of course, because that's coming from the Q-sum transformation of the mean. But if you view the Q-sum transformation of the whole data as a perturbation of the Q-sum transformation of the mean, so viewing T as the perturbation of A, then a natural way to estimate V would be to take the kind of the so-called leading left k-sparse leading left singular vector of T. We're basically looking for vectors, unit vectors U that are k-sparse that maximizes U transpose T in L2 norm. And it's not too difficult to show that this k-sparse leading left singular vector estimator does pretty well in estimating the oracle projection direction V. And we can show that the key point here is that the dimension P only enters this sine angle loss. So the sine angle loss is the sine of the angle bounded between the two vectors. The dimension P only enters the loss logarithmically, and this bound is with high probability bound. So that's a very promising direction. The only catch here is that it's NP-hard to actually calculate the k-sparse leading left singular vector. However, the discussion we had on the previous slide was not completely wasted, because it turns out that we can somehow relax this non-convex problem, because it's a non-convex problem. That's why it's NP-hard, to something that's convex and that's computable. And the idea is to lift the original vector optimization problem into a matrix optimization problem. It's called the idea is called semi-definite realization. So essentially, let me briefly describe this here. We're maximizing the L2 norm of U transpose T over the set of unit vectors with k-sparse entries. We can rewrite this as maximizing U transpose TW, where we stick in a W that's another unit vector, and then treating U transpose TW, which is a scalar, as a 1-by-1 matrix, or as the trace of the 1-by-1 matrix. We can rewrite this as trace of W U transpose times T. So using the cyclic invariance property of trace. So trace of AB is equal to trace of BA for matrices. So this notation, bracket notation here, is just a so-called trace inner product between matrices. And then if we view this UW transpose as a whole, as a variable, we can rewrite the optimization problem in terms of a matrix optimization problem for matrices M in this set. So everything here is equality, which means that if the original problem is non-convex, there's no way that the final problem can be convex. However, what we have achieved is that we have removed the kind of a non-convexity in the objective function, because originally we're maximizing a convex function, which is a non-convex problem. And now we are maximizing a linear function in the matrix M, so that's a convex problem. So the only non-convexity is contained in the feasibility set curly M here. And I've highlighted out that there's a rank constraint and a number of non-zero row constraint. What we are going to do is that we're going to enlarge this set curly M to something that's actually convex, so kind of convexify it. And well, it turns out that we can drop the rank constraint and replace the number of non-zero row constraint by a kind of a entry-wise L1 norm constraint. And it turns out to be easier to analyze a penalized version of the L1 constraint rather than the constrained version. Just like in sparse linear regression, we want to do a kind of a penalized lasso rather than just a constrained lasso. So this is the final optimization problem we want to solve. And once we solve this problem, we can find an estimator of the projection direction by looking at the leading left singular vector of the matrix M hat. Okay. So this problem, as it turns out, is now convex because we're maximizing a concave function over a convex set. And the problem itself can be solved using something called ADMM, alternating direction method multipliers. It's polynomially computable. However, it's still quite slow for large data sets. What we can do is that we have already enlarged the feasibility set to curly S1. Maybe we can enlarge it even further if that simplifies the computation. So if we replace the original nuclear norm constraint in the definition of curly S1 by a Frobenius norm constraint, so the subscript 2 here represents entry-wise L2 norm of a matrix, so that's the Frobenius norm. It turns out that the optimizer of this problem has a closed form expression where we're just doing some soft thresholding of the Q-sum transformed matrix T by a level lambda. And that's a much nicer expression. We can kind of compute it very quickly. Of course, the optimization problem we're solving is further away from the original non-convex problem, so we will incur some statistical efficiency loss. So there's a statistical and computational trade-off involved in this problem here. using either the kind of a relaxation using curly S1 or the relaxation using curly S2, as I mentioned earlier, we can estimate the projection direction by the leading left singular vector of m hat. And this proposition here gives a theoretical bound guarantee on how close the v hat is to the oracle projection direction v. And I mean, if you remember the expression that we saw earlier for the non-convex optimization estimator v hat k max, this is essentially the same bound, and with slightly worse constants. So we are not losing that much by kind of relaxing it to curly S2 even. So now we have an estimator for the oracle projection direction, the optimal projection direction. We can put it together into an algorithm for estimating the change point. So basically, every single step here, we've already seen. In step 1, we do the Q-sum transformation of the input matrix X. In step 2, we solve the optimization problem to get a matrix optimizer m hat. In step 3, we kind of get the vector projection, the estimated vector projection, using this optimizer m hat. So in the final step, we project the Q-sum matrix along this direction to get a univariate Q-sum series, which we write as T bar here, and look for the location of the peak of this univariate Q-sum series, and that's the estimator of the location of the change point. So that is z hat here. For the later reference, we also output the magnitude of the peak. This is called T bar max. So T bar max is useful in determining whether the estimated change point is really a change point or just a spurious one. So we want to do some kind of testing here to kind of just determine whether, because even if there's no change point, the algorithm will output a z hat, but we want to determine whether that's a true change point or not. So this slide gives a theoretical guarantee to the estimation quality of z hat. Essentially, under the condition where the projection direction estimator v hat is consistent, so we don't even need this to be consistent. We just need that non-trivial proportion of the signal. So it's kind of like the angle is not perpendicular, basically, to the truth. We can show that the loss here, z hat minus z divided by n, is converging at the rate of sigma square log n divided by n var theta square. And we can show a minimax lower bound to show that this is actually the best you can do up to log vectors. Right. So that's the story for estimating a single change point. Then we moved on to kind of use the single change point estimation procedure to estimate multiple change points. I'll just briefly describe, because this is basically a kind of a well-known idea called binary segmentation. So essentially, we pretend that there's only one change point in the whole data set and use the single change point procedure to identify where that is. And then we split the data set into 2 halves and repeat this procedure until the T bar max score, if you remember, is below a certain threshold. So we terminate the recursion. So this is called binary segmentation. There are a few problems with the kind of vanilla binary segmentation. One thing is that multiple different we are pretending there's only one change point, but multiple change points may offset each other. That can lead to a loss of power. And also, we are assuming that the kind of change points are sparse, but different change points can be sparse in different coordinates, and misaligning the change coordinates can be bad in terms of getting the right projection direction. So they may have some kind of confounding with each other. So to resolve this, we use the so-called wild binary segmentation scheme from the Frislevich 2014 paper. Essentially, the idea is that we generate a large number of time windows at the very beginning, and then we compute single change point estimators within each time window, and choose the time window that gives us the largest T bar max score, and call that the best candidate change point location, and do the split along that candidate change point. And then when we split the data, we only use time windows completely falling within the left and the right to do the recursion. And we have some similar stopping criteria to terminate recursion in the end. So this is the full algorithm. We call algorithm INSPECT, I think standing for informative, can't remember, sparse projection estimation for change points, I think. And it's available in the INSPECT changepoint R package online. And this is a kind of an action of INSPECT, for a data set. I think in this case here, n is 2000, p is 200 or something. And then there are actually 3 change points, one at 500, one at 10,000, sorry, 1,000, one at 1,500. It's very difficult to visually see them, but because the magnitude of change are actually quite small, and then they're only kind of supporting a very small number of coordinates, you can kind of visualize the last one here. But INSPECT managed to pick the 3 of them out quite well from the kind of the remaining ones down here. So like the single change point, we also give theoretical guarantees to the multiple change point estimation, and we can show that with high probability this get the number of change points correct, and the rate of convergence for each individual change point is this row here, which depends on lambda. So the lambda is a log factor, and then after log factor, this is 1 over n times var theta squared times tau to the 5th. The rate is minimax optimal in terms of n and var theta, but it's not in terms of tau. I think we suspect that the suboptimality may be inherent in any Q-sum-based methods, actually, for multiple change point estimation. Due to time constraint, I'll skip through the numerical studies. Maybe I'll just talk about the talk about the multiple change point estimation. So here we compared our method to a few existing ones in the literature. And then, so this is an example for multiple change point estimation. We have 3 change points. It's essentially the picture that you saw earlier. And then the signal to noise ratio is in the ratio of 1 to 2 to 3 at the 3 change points. And this is the kind of the histogram of estimated change point locations after, I think, 100 repetitions. And you can see that the INSPECT actually estimates the kind of most obvious change point with much higher accuracy than the competing methods, and it gets more of the kind of the less obvious change points right, because in some of the methods like the scan statistic based method, I think a lot of times this change point is not declared. Still, though, this somehow seems to have more false positives that's not really related to the actual change point locations, and we're trying to improve the method to kind of try to reduce these false positives at the moment. Right. How much time do I still have?
I think maybe we can wrap it up.
Yeah, I'll just wrap it up. Right. So just to kind of give some future directions where this research can go. So basically, one difficulty that INSPECT have, I think, is in handling non-trivial unknown spatial correlation. So if the coordinate, we're assuming that the coordinates are actually IID with kind of a normal 0-1 noise. But if there's some strong spatial correlation between the different component series, then I think at the moment, INSPECT will declare too many change points. So we're thinking about ways of handling these spatial correlations. And also, there may be additional spatial structures in the signal. For example, that the signals may be clustered in spatially nearby component series. And another thing is, of course, to move this from the offline to the online setting. All right, thank you.
Thank you very much, Tanya. Now it's the discussion time. So discussion time will be kicked off by Claudia. So Claudia, it's all yours now. Thanks.
Thank you very much. Also, thanks a lot to Paul and Teng Yao for giving 2 quite interesting talks. Maybe because we all have Teng Yao's talk in mind, I just start asking questions for that talk. And maybe I just start with the obvious question here. Clearly, at the beginning of the talk, you made several assumptions. You assumed Gaussianity. Then there was an independence assumption, both in time as well as across components. And on top of that, there was this equal variance assumption in all of your components. So my question is, how strongly do your proofs depend on that? And which ones do you think are more difficult to relax and practice? And which ones aren't?
I see. So let me do them one by one. So I think the first thing about the Gaussianity assumption is it's not really important in the proof. So the only reason to put it there is just to simplify the arguments. The reason is because in the Q-sum transformation, the way we analyze it is to look at the Q-sum of the mean and Q-sum of the noise separately. And in the Q-sum of the noise, essentially what we get is that something that looks like a normalized Brownian bridge. So if you have something, as long as you have enough moments, you can use a kind of a Brownian embedding kind of argument to say that as long as you get rid of the beginning of the end and the end of the series, you have something that looks more or less like a point on the Brownian motion. And so the basic idea is kind of some kind of central limit theorem will hold, and then you don't really need the light-tailed condition on the noise in that case. The condition on the known variance is also not too crucial, because we're basically saying that in each component series, the noise are roughly of the same level. If you don't know the variance beforehand, what you can do is you can take the finite differences, the kind of consecutive differences between the points, and then use that to get a robust estimator for the standard deviation within each component series and normalize the series accordingly. So because we only have a very small number of change points, so for most of the differences between, let's say, the first data point and the second data point, the difference is in, let's say, the first coordinate is going to follow a normal 2 sigma square distribution. So you can estimate sigma quite consistently using that approach. The more difficult question would be about the independence assumption we used there. So there are really two different kinds of independence that we use. One is that we're assuming that there's temporal independence between the observations. So this makes this kind of a less classical time series because there's no temporal dependence involved. What we showed in the paper was that as long as the temporal dependence is short-ranged, it actually doesn't really matter. Basically, we don't need to change the procedure. So the procedure can stay exactly as it is. And it's just the theoretical guarantees needs to be slightly modified. And that actually bores out in the simulation studies as well. And then there's the spatial independence assumption between the component series. That's actually more difficult, actually. So what we can allow is kind of a short-ranged spatial dependence. So we need to, if we assume that the kind of a dependence are very local in the sense that it decays exponentially as the distance between points are far away from each other, then we are in good shape. However, if there's some sort of global spatial dependence, for example, there's some, let's say that the covariance matrix is 1 on the diagonal and alpha everywhere off diagonal, then the performance of the inspect will be quite significantly affected. And specifically, it will declare more change points than there should be. And also, the projection direction estimator is a bit wrong because it's not really estimating the optimal projection direction. For different covariance matrix, you can show that the projection direction needs to be slightly changed depending on the covariance matrix. I mean, if we know the structure of the covariance, we can obviously estimate that. But in many cases, in applications, we don't really know that. So I think there are a few recent works on using things like factor models in conjunction with change point estimation to remove this global spatial dependence structure. Another direction I'm currently thinking about is using ideas from Gaussian multipliers to generate kind of a multiplier bootstrap sample of the original data series, and use that to calibrate the kind of the threshold level for the T-bar max scores, and that will at least solve the issue of the inspect algorithm declaring too many change points. It won't solve the issue of finding the kind of the correct projection direction, but at least it won't kind of it will make sure that the inspect algorithm will not declare too many false positives. Hopefully that answers the question.
Yeah, thank you very much. And in fact, it very much coincides with my own experience with other procedures. So I think this is probably basically not only true for your procedure, but for many others as well. So they all face the same problems effectively. Mm-hmm. Let me ask you one more question, and then maybe I go to Paul and ask Paul a question. If you look at your multiple change point problem, then you see that basically this is not important in the single change point problem. This is why I mentioned this. You see that you are assuming effectively, or this is also the way you formulate your result. You are assuming that all of the change points have the same lower bound for the signal strength, which was theta, and the same lower bound for the run length, which was tau. But this effectively means that, and then you get the optimal rates for this. But this effectively means that all of the change points are, well, of the same kind, in the sense that of the same order, yeah. But in reality, of course, you could have a situation where you have one change point that is relatively small, but has long stretches of stationarity around it, and that would be detectable with a good rate. And at the same time, you have a maybe big thing with just small stretches of stationarity. But then if you want to mirror this in your theoretic results, you would need to go over to signal strength theta that actually depend on I, and run length tau that also depend on tau. And then you would need on I, sorry. And then you would basically need to get the rates where it comes into play the theta I somehow in the result. So we would need to see the result to show you exactly what I mean. My question is, have you looked at that?
Yeah, that's a very good question, actually. So, so we looked at a related problem where, let's say that every change point are above theta, above tau in terms of the signal strength and the run length, but for some they're actually much higher. So we can actually show that for those change points that are higher, the rate will actually be kind of you get a better rate for those more obvious change points. But what you're asking is slightly different, I believe. You're saying that there may be some trade-off between the length of stationarity and the magnitude of change. So at the moment, let me think. In the proof, I believe we do need to assume that kind of the var theta and the tau are the same for all the change points. The main reason is because we use the wild binary segmentation, and in that we need to have sufficient number of time windows so that there will be kind of at least one time window capturing each individual change point. So if some of the kind of change points have a very small time window but with a large signal, then that means that we need a very large number of time windows to just capture that single change point. So I'm not sure if there's an obvious fix that can allow for the theory to be extended so that instead of assuming a lower bound for var theta and also for tau, we can assume a lower bound for something like a var theta squared times tau, right? So yeah, I'm not entirely sure if there's an easy fix to the proof that can allow for a single lower bound on the kind of on the signal strength. In terms of the empirical performance, I'm also not really clear about this point because I think I need to do more simulations to see whether this is also this is effective in practice or not.
Okay, thanks. I think in empirical studies, maybe this is not. I think it's probably working nicely. It's just a question of whether theory is also possible to do or not. But thank you.
I see. Thank you.
Okay, so maybe now I ask Paul a couple of questions, and yeah, so this was a Bayesian online procedure, and maybe we can somehow compare a little bit about the sequential and non-sequential setting there. So for me, it was, I mean, Paul also mentioned at the very beginning of his talk that it's important to choose the right prior, and that it's not entirely clear how to do this in the online procedure in order to get good results. And then you presented a particular prior to us. And my question is there any kind of a relationship between that prior and something that you would be using in the Bayesian offline procedure?
Okay, so I tend to think, so in some sense there's like two key priors you specify. One is the prior for the segment-specific parameters, and one is for the sort of segmentation. And I don't know whether your question relates to one or the other. I mean, the way these methods deal with the sort of prior for the segmentation is that it's most natural to do things in terms of modeling segment lengths, whereas maybe a more standard MCMC approach, offline MCMC approach, the most natural way would be to have a prior on the number of change points and then conditional on the number of change points of prior for where the changes occur. Now, often there can be an equivalence. I mean, so certainly a prior on the number on the segment lengths would imply a prior for how many change points there will be and where they occur. And often that corresponds to the sort of natural priors that people do choose when they do MCMC. Having said that, I think there are also other priors that people use where there wouldn't be a correspondence, but my experience is that those differences don't tend to matter too much in terms of the results. Probably the main thing that matters is the prior for the segment parameters, which in some sense that you know, you can imagine having essentially the same prior in a online setting as a sort of MCMC type setting. And probably the only thing that really matters in terms of the prior on where the change points are is just sort of details about how it deals with very short segments. You know, but my experience is that what really matters is the prior on the segment-specific parameters.
Okay, thank you. Now, from what you have presented, I understood that at the end of the procedure, you had a posterior distribution. Basically, for every t, you had a posterior distribution for, let's say, when the last change point, the location of the last change point. But what you want in the end is you would like to have, and of course, from that you can get an estimate of a probable last change point, let's say, from where you stand. But in the end, you want to have a sequence of change points. And how do you get that from the sequence of posterior distributions?
Okay, so maybe there are two things to say is that probably in most online applications, the only thing you may be interested in is where the last change point is. So for example, if you have some online application and you're doing forecasting, often your forecast will only depend on the data up to the most recent change, and therefore if you have the current posterior for where the most recent change is, you can do whatever you want to do in terms of forecasting. More generally, if what you actually do care about is the posterior for all the change points, it is actually very simple to simulate from that joint posterior just by simulating, so you've analyzed the data up to time t, you have your posterior for the last change point in your data set, so you can simulate from that, and that will give you a draw for the last change point. And then you go back to that time, and then you can sort of simulate from the distribution you calculated, which will be when's the penultimate change point, i.e. the last change point prior to the one you just simulated. And you can just recursively simulate back change points one at a time. And in doing that, until you get back to the beginning of the sequence, that will give you a random, a realization of a random number of change point locations, and that will be a draw from the full posterior.
Okay.
Now, yeah, I mean, there is a further challenge then of, well, if you want to, I mean, that gives you a draw from the posterior. If you want to, you know, represent that, like have some point estimate or whatever, then there are sort of complications, because it's quite a, you know, given lots of draws from the posterior, each of which may have many different numbers of change points, how do you summarize that? It is still quite challenging, but at least in terms of simulating from the posterior, you know, it's straightforward.
Okay, thanks. And but what I'm curious about is this posterior is then you end up with the full posterior, but this is based on the sequential procedure that you put up. Instead, you could have done an offline analysis up to that point, of course, and come up with the posterior. And somehow I would expect that the latter is somewhat more precise, but of course, there are good reasons why you did the online thing. This is beside the point. But the question is, as compared to the to this offline thing, how much do you think you lose? Or I mean, I don't know. Maybe you haven't looked at it because you were actually interested in the online setting for other reasons. But it's still interesting to see how much does one lose if one doesn't look at it in this way.
Well, so if you analyze, you know, if you have a fixed data set and you either run some offline, say MCMC, to sample from the posterior, or you run this online procedure and you use this algorithm to sample from the posterior, then providing the, you know, the model and the priors are the same, you're going to, but both methods are going to be sampling from exactly the same distribution, so you don't lose anything.
Yeah, but the question, they're probably not exactly the same, though, are they? I mean, because at each point when you calculate, you're only using part of the data. And so, while otherwise you could have used more data. So, I mean, maybe they are, but I was just thinking that probably they are not exactly the same. So you would use something that is somehow using more information if you do an offline setting, and then it should be more precise. But question is, but maybe that's not true. So
Yeah, so I think, well, so the models that I considered had this conditional independence property. And so that, because of that, you have the same posterior from the online algorithm as an offline algorithm.
Okay.
Just because, you know, if you think about, you know, if you simulate your last change point, and then to simulate the penultimate change point, you know, so say you simulate the last change point at some time t, and then to simulate the penultimate change point, you simulate from the filtering distribution for the most recent change point prior to t, given the data up to t. Well, it turns out that that's actually not throwing away any information, because of this, you know, conditional on there being a change at t. What happens prior to t, in some sense, is independent of what happens after t. So it's that conditional independence property means that the online algorithm is using, you know, is sampling from the same posterior as the offline.
Okay, thank you. Thank you, Claudia and Paul and Chen Yao for the discussion. So we don't have much time left, but I was just wondering, is there any question from the audience who hasn't really unmuted yourself yet?
Paul, it's Richard here.
Hi.
Hi, Paul. So let's suppose I do the following. Let's suppose I kind of just treat your Bayesian model as a motivation for coming up with an algorithm for online change point detection. What are the prospects for then just treating that as an algorithm and trying to understand under what data generated mechanisms can one recover change points, and what the kind of the delay would be in doing so? Does that make sense to the question?
Yeah. So that, I mean, that would be quite a sensible thing to do. I don't have any experience as to how easy it would be to analyze. I mean, my guess is that well, I mean, if what you're interested in is how quickly you detect a change, then my guess is that it may be possible to come
a guarantee on the false alarm rate, I think.
Yeah.
Yeah.
I mean, I think those sorts of problems have been studied to some extent in the sort of sequential change literature, and at least some of those methods have a very sort of Bayesian interpretation, in the sense that, if you look at, so essentially the main difference would be, rather than you consider a change at each previous time point, and rather than sort of looking at the maximum sort of those, as you often would do in a sort of more likelihood-based method, you do some sort of averaging of those to give your evidence of whether there's a change.
So how feasible do you think it would be to take the kind of Gaussian-Van der Waals type theory and extend it to a sequential setting?
I don't really feel informed to say. It's not something I've looked at, so I wouldn't know.
That might be quite an interesting direction, I think.
Yeah.
Thanks everyone for joining us today, and thank Paul, Changyao, Claudia, and Richard for all these insightful talks and discussions.